Okay, let's look at the topic of, now coming back to the topic of Verilog, right? How do we write sequential test benches in general? Do they differ from the kind of test benches that we would write in combinational logic? In some aspects, yes, but in a lot of aspects, a test bench is a test bench. I mean, it's just that you need to essentially make sure that you now recognize that there is a clock and see how we can make use of that factor. There are a couple of important things, of course, that come in the context of a test bench, which is that when you declare a test bench, you also need to know how am I actually going to define and use a clock inside it. So first things first, since the clock is generated inside the test bench, it's usually defined as a register, or in system Verilog, of course, things are simpler, you just call it logic. The simplest, the first method that we can use is what's called a simple toggle, right? Essentially what it says is always after 5 nanoseconds, clock is equal to tilde clock, okay. Now this is actually a very simple and neat way of defining a clock. It's like a one-liner, right? And effectively what it says is that every 5 nanoseconds I flip the value of the clock, goes from 0 to 1, 1 to 0. So which means that one complete cycle, 0 to 1 and then back to 0, will take me 10 nanoseconds. Therefore, the clock frequency is going to be 100 megahertz. Okay. Now understand that this is just something we are creating as an artificial test case in a test bench. Remember that putting delays into logic has no physical meaning in terms of synthesizability. So having a delay like this in a test bench does not necessarily mean that your circuit actually works at 100 megahertz. So just putting in a delay and saying I simulated it at 100 megahertz and it worked means absolutely nothing. In fact, you could make this 0.5 and then say that I simulated at 1 gigahertz, it means nothing, because the actual circuit that you have designed over there, unless we are able to account for the individual gate delays of every single element that after it gets synthesized, it does not really have a practical meaning. That comes later, right? We are not going to talk about it now. For the time being, all that matters is, as a matter of convention, we usually try to apply like a 100 megahertz clock because it keeps our numbers easy to understand, right? It's very easy to think in terms of multiples of 10 for the clock period or the number of clock cycles that have passed, right? Okay, now there's one problem with this always block, which is that how do I make sure that the clock value starts from 0, okay? And for that, what we actually need to do is we will need a separate initial block in which we will say clock is equal to 0 to start with, right? Once again, initial blocks are fine in test benches, they don't make any sense in synthesizable hardware, or at least not in general, but in a test bench it's perfect, right? You can set clock equal to 0. But now you notice that you had an always block and an initial block and you have clock being defined in both. What about that multiple driver problem? Again, not an issue, this is not synthesizable, we don't care about multiple drivers. The initial block fires initially, that is when the simulation starts at time 0. It creates an event at time 0 and therefore it initializes clock is equal to 0. This always block takes over after that and every 5 nanoseconds triggers an event that is going to basically change the value of the clock. That's it. Okay. On the other hand, if I am anyway doing this initialization of clock equal to 0, I could also use this forever and say clock is equal to tilde clock in here. This also works as a way of defining a clock. This is a very common way of doing it, right? But it still requires you to do the initialization, which is usually not a problem because you need an initial block for other reasons anyway, like the reset and the data input. What about reset sequencing, right? Reset is an explicit signal that needs to be generated somewhere in the test bench. Usually what is done is, inside the initial block that takes care of all your data, you start off by initializing the signal, right? And you say reset n equal to 0. Remember, this is reset n, it is active low. You want to initialize it to 0, right, to make sure that it sort of goes into reset. It's also a good idea to sort of initialize the data values that you have at the same point. And now the interesting thing about Verilog is things like repeat at passage clock. Now what does this mean? It's interesting. All that it says is this, just an at passage clock without anything else, basically says create an event at the next positive edge of the clock. Okay, That's if I did not have this reset, this repeat 5 over here, just the add passage clock. What the add passage clock means is create an event at the next positive edge of the clock, wait until that event and then proceed further. Okay, so it's another way of writing wait for passage clock, right? There is a way of writing wait also in Verilog, and VHDL also has something similar. This is basically sort of waiting until that event happens. Now repeat 5 basically says wait for 5 clock edges, okay, and this is common practice because even in real scenarios what we usually do is once we apply reset, we try to hold it for a significant amount of time, usually many microseconds or possibly even milliseconds, to ensure that everything in the circuit has had a chance to get reset properly, because not resetting can very often be the source of multiple problems inside actual practical circuits. So while we are doing the simulation, also we do the same thing. We typically just hold it active for a few clock cycles, then release the reset, right? Take out the reset, make it 1 and wait for a couple of cycles. Why should we wait for a couple of cycles? Well, it's not absolutely necessary, but again this sort of models what would typically happen in practice. The moment you come out of reset, you are not immediately chugging away and doing things with the data. Having said that, if you are, for example, working with a microprocessor, as soon as you release the reset, the microprocessor is going to start working, meaning that it will start generating addresses in memory from which to read instructions. Okay, and it's as simple as that. It basically goes ahead, it does not even need you to wait for anything. But in this case, since we are trying to feed in data, we decide, okay, let's wait for a couple of cycles and then start to apply our test sequence. So this is the typical structure of how reset is used in a sequential test bench, right? What are the crucial things? We have reset, which is required for sequential logic. We are able to wait for clock cycles. We typically, after removing reset, we wait for a couple of clock cycles before changing data and so on. These are just common aspects that we follow. As already mentioned in an earlier video, right, you can use tasks and functions to make your life easier in terms of how you write code. An example of a task could be basically wait for a clock edge, apply data, apply valid, wait for another clock edge and then make the valid 0, right? And that basically allows you to write data very neatly and compactly, test benches in a very compact manner. You can basically wait until the reset condition has been taken out, right? And then afterwards call this task out here, which says write data, which would take this hex AA value as input, wait for a clock edge, assign data in, make valid 1, wait for another clock edge, make valid 0, and then get ready for going to the next write data task. Similarly, you can also use functions, right? And functions would, for example, be used in order to do things like checking whether a certain output has a correct value. You might notice for over here that this also has a couple of keywords like automatic and bit. These are sometimes used in order to specify. The bit is basically the return data type, once again system Verilog, and automatic is something which is not strictly required, and it's something more related to, it is similar to the idea of automatic and static variables in language like C. For the most part, if you find that you actually need to write code of this sort, then you hopefully know enough Verilog by that point to know exactly why you are doing it, right? But at least for the kind of things that we will be looking at, you should not normally need to write code of this sort. The important point, of course, is in a test bench you can have any kind of function. You can even have recursive functions, right? And automatic, for example, is required in order to have the ability to write recursive functions. But you should be very clear that you do not put such kind of functions into code that is meant to be synthesized. That does not mean functions cannot be synthesized. Functions can help you to write code in a certain way such that computation can be expressed in a very clean manner, right? And may still end up being synthesizable as long as the logic it is doing is fairly straightforward. But if you try doing something more complicated, and especially if you try doing something like recursion in a synthesizable code, it is almost certainly not going to work.